So here's the question I asked at the end of the previous part of this lecture, and hopefully you understand that the acceleration is straight down. After it's released from the plane, this package is a projectile, and its initial velocity is just the velocity of the plane. And so that tells us that VI is directly to the left. And so the answer is A. Remember, in the motion in a straight line unit, we had these equations for motion with constant velocity. And in particular, at the time, I pointed out that we can write them as a single vector equation or as a pair of component equations. And what makes them so easy to work with is that we have one equation which only involves x and the x component of velocity, and another that only involves y and the y component of velocity, and so Vx has no effect on y and Vy has no effect on x. In other words, the x and y components of the motion are independent of each other, and that makes the motion much easier to think about. Now, I will warn you that this is not always true. However, the cases where it's not true are very complicated, and we're not ready for them yet. And furthermore, how to tell whether the x and y components of motion are independent of each other is also very complicated. So for now, I will just leave it at saying that this is true for uniformly accelerated motion, just like it's true for uniform velocity motion. And so that's going to be very helpful to us because it means that the uniform accelerated motion equations can split into two component equations which are independent of each other. Now we can understand something that I hinted at way back near the beginning of this lecture, which is that the perspective riding on the cart is simpler, and now we can see why. We can think of this motion as two one-dimensional motions superimposed on top of each other, a vertical motion with uniform acceleration and a horizontal motion with uniform velocity. And by taking the perspective riding on the cart, we simply remove the piece that's horizontal. To start to see how we think of a 2D motion as two 1D motions, let's return to this falling object. And one way of thinking of vector decomposition is that we are projecting the vectors onto the x and y axes. So here are those two velocity vectors projected onto the x and y axes, which give us the x and y component vectors. And we can similarly project the acceleration vectors onto the axes. In this particular case, the acceleration is parallel to the y-axis, and so its x component is 0, but more generally, we'll end up with x and y components of the acceleration. Now you can see, looking here, how this looks like a nice 1D motion with an acceleration in the direction of motion, and thus it's speeding up. And this looks like a nice 1D zero acceleration motion. And we can now think of this motion as being made out of these two motions going on at the same time. And we've reduced the problem of thinking about a 2D motion to the problem of thinking about two 1D motions. So, because the acceleration is constant, we'll get to use our old familiar uniformly accelerated motion equations, except that we're now in 2 dimensions, and so we have to use their full vectorial forms. Well, the first two UAM equations are vector equations. Here they are written as vector equations, and so the first one will separate out into two component equations like so. And in the first one, we note that for a projectile, AX is 0, and so that turns it into a rather trivial equation that isn't even particularly useful. In the second equation, that acceleration is plus or minus g, and I'm saying plus or minus because it depends on which way you've oriented your y-axis. And similarly, the second equation separates out into two component equations, and once again the acceleration part drops out of the x component of the equation, and in the y component we know that acceleration is either plus or minus g. The third UAM equation, though, is not a vector equation. Look at it. It appears to involve multiplication of vector components by other vector components. And so there's something going on here with vectors multiplied by vectors. Now we know how to add and subtract vectors, and we know how to multiply a vector by a scalar. But we don't yet know how to multiply two vectors together. And so for now, all I'll say is that even though this isn't a vector equation, we still wind up getting two independent equations anyway. The first one, again, is trivial and totally useless, but the second one we can use. Actually, working projectile problems is fairly straightforward. It's just uniformly accelerated motion after all, but it is also rather detailed and time-consuming, so I'm not going to work any problems on it in this video lecture. I will post a supplementary video lecture where I'll work one or two for you. Let's check your understanding of this so far. So suppose we know the initial velocity and initial height of this projectile, and we're going to call the final time the moment of impact. In that case, what is the final velocity of this projectile? As usual, if you're doing this through Moodle, it will ask you this question. Otherwise, you should still try and answer it before you move on to the next part of the lecture.